Thank you for joining us today. This is the last event of MDENet for this year, and funnily, it has so happened that it's me doing it. I'm Steffen Zschaler. I'm the director of the MDENet network, but also an academic at King's College London, researching various aspects of model-driven engineering. And in today's session, I want to talk a little bit about how to make domain-specific modeling languages do something in a sort of interactive way. And I'm hoping for this to be a bit of a training session in that you get to interact with me a little bit throughout as well. Although it's not going to be quite as interactive, I think, as Antonio's session last time, just because the tooling's a little bit more complex and a little bit more difficult to make sure that it works correctly for everyone in the room if we're not actually in the same room. And so rather than spending a lot of time fixing everybody's setup, I figured it may be easier to run it as a sort of live programming session, as it were, with you, with us interacting a little bit, talking about what we would do next and what the next steps would be. So what are we trying to do today? What I'm going to try and talk about is how we can use the GEMOC Studio in particular, together with Sirius and some other little bits and bobs, to first of all build a simple visual domain-specific modeling language, visual concurrent domain-specific modeling language. I'm going to say something about what the concurrent bit means here, and how we can build a debugger for that modeling language at the same time. Importantly, I think what I'm going to talk about is how to do that using declarative tools. So with what I will claim is sort of minimal effort for building all of this sort of environment. Okay. So what is the language that we're going to be building? I thought it'd be fun to build a little language that allows us to model how passengers move through an airport. And it's a very, 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 very simplistic domain, right? So we've only got an hour for this session, so I figured we need something that's very simple. So it's not actually a language that would be particularly useful yet in the real world because it's so narrowed down. But what it allows us to do is to model things like check-in desks in an airport and queues of passengers, where passengers can queue for those check-in desks, and then talk about what the semantics are of this language. So how do models behave, which is really about passengers moving through this airport, joining queues, going to check-in desks, and then moving on further into the airport. And then from that you can see how we could extend that to support additional aspects of the airport, to allow us to do additional analysis of, for example, different setups of an airport check-in area, and possibly do some simulation-based analysis, for example, for performance and throughput kind of questions, or for security questions, etc. But that's not something that we're going to cover today. The link at the bottom here points you to the GitHub repository that has all the code and models that we're going to build during today's session as well. So one key thing that I want to talk about in particular around today's session is this idea of model debugging. Just like with programming languages, debugging is an interesting and important thing, because getting models right, and even getting modeling languages right, is a difficult thing, just like with programs. So it becomes easier if we can play with something, if we can try things out, if we can animate those models and just experiment with them. But building language IDEs is hard already, right? And building debuggers basically means we've got to do even more, right? So it's even harder. And what I'm trying to do today is to show you that it doesn't have to be extremely hard, and that there are tools out there and how you use them for building debuggers just together with an IDE for your new language. By the way, I should have said, at any time, if you have any questions, you want to ask something, you want me to explain something in a different way, please just either put something on the chat or raise your hand or something like this. I am able to see sort of the team's view as well. So if there are questions, I'm hopefully be able to pick those up. So I've said IDEs, building IDEs and stuff is hard, but of course one of the key things that have been explored in the context of MDE research is this idea of a language workbench, which is all about making it simpler to build new languages and to build support environments for those new languages. And the key idea behind a language workbench is essentially to take a model-driven approach to the development of new languages, new domain-specific languages, where we start with a high-level description of our language here on the left, and then we have a generator-based infrastructure that generates editors, IDE integration, possibly builds code generation infrastructure for us, and as we'll see today, possibly builds debuggers for us. And with such a language workbench, it actually becomes possible to become relatively agile in developing your new languages. And therefore, you know, ideas like language-oriented programming, where you sort of build your language as you build your software, become actually feasible and come into reach. So if we are going to do a declarative description of, or a high-level description of our language, what are the bits that we need to describe? We need to talk about these three aspects of our language. We need to talk about our abstract syntax, which is sort of what are the concepts in our language, and how are they related? So what does the language talk about? We need to talk about our concrete syntax, which is about what does the language look and feel like? How do we interact with the language? Is it a textual language? Is it a graphical language? Is it tables? What's the visual structure, and what's the interaction that we have with this to edit models and to create models? And we need to talk about our semantic domain and the semantics of the language to sort of say, what do models mean? And you see these arrows here, they sort of show how these things interact. So the concrete syntax builds on top of the abstract syntax, and the semantics also build on top of the abstract syntax. So the abstract syntax tends to be at the heart of our language. What I'm going to do today is I'm going to show one way of instantiating this diagram. So I've said these bits already, I think. I'm going to show this by using a particular set of tools for describing these various bits and pieces. We're going to use the Eclipse modeling framework to describe our abstract syntax. We're going to use Sirius to describe the concrete syntax, which means we're going to build a graphical domain-specific language, so with a graphical visual concrete syntax. And we're going to use Henshin to describe declaratively what the semantics of our language are. And all of this is tied together in this GEMOC studio, which allows us to bring these various bits and pieces together. In particular, allows us to bring in a description of the semantics of our language, and from that generate debugging support for our language. I'm cheating a little bit here. I'm going to use GEMOC studio with a small extension for concurrent languages that I think should be in the nightly build now. And I'm going to use there's a specific engine for semantics, which is this Henshin-based engine, and I've put the link to that in here. For that, there might be some small dragons if you want to install this on your own, and if you struggle with that, please do contact me after the session, and I'll be happy to help you get it to work. Let's start, as I said, with the abstract syntax, because that's sort of at the heart of our domain, of any domain-specific language, really. So defining the abstract syntax is typically done using so-called metamodels, and a metamodel is basically you can think of it as essentially a class diagram of all the concepts in our language and the relationships between those classes. And from that, if we're in the Eclipse world and the Eclipse modeling framework world, what we do is we create this class diagram, and from that we can generate a bunch of code that allows us to basically just store models in memory, load them from files, write them to files, and have a very basic editor for them. That allows us to just manipulate models in a very basic fashion already. And so that's going to be our first step, and then we're going to build on top of that. So let's try and do this. So here is my GEMOC studio. And please, again, shout at me if you find that you know this is difficult to read or anything like that, then please let me know, and I'll try and make some changes to the sort of font sizes and things like that as far as I can. What we're going to do is we're going to good. So Antonio clearly has very good eyesight, so he says it looks good to him, so that's great. what we're going to do is we're going to start by creating a project. So everything in Eclipse is a project, right? So everything we want to do, we do in a project. We're going to create a few of those projects over the course of today's tutorial. We're going to create an equal modeling project, which allows us to create a new meta model. Just as a general point on the structure, what we're going to do is I'm going to talk us through a few steps together with you, and then I'm going to step and pick up a pre-made version, just so that I don't mess myself up with typos and things like that, and we don't get into a mess later on. So let's create one of these projects, and let's just for now just call it airport meta model. And no, oh well, actually maybe not. And that's fine. And then we say we want to use this design version, so that allows us to create class diagrams directly. No, stay where you are. That's fine. Okay, so what we're going to do is in a moment we'll have a class diagram here, and I can tell my computer's struggling a little bit, so I should give a warning. My computer doesn't really like to run Eclipse and Teams at the same time, so sometimes it'll complain and I'll go stuttery when Eclipse actually does some work. So we have a class diagram in here. What we want to do is, for our language, we need to now define the key concepts. So my first question to you is, what do you think are sort of the key concepts that we need to worry about in this simple language? And to make that easier for you, let me go back a little bit. Come on, and show you again. This is sort of a visual view of what sort of models we might want to support. So if you have any ideas about what concepts we should have in our language, either say them on the microphone or just put them into the chat if you wish, and then we'll look at them. Any suggestions? Okay, so Antonio has some interesting suggestions here. He suggests we need an airport, we need a passenger generator, we need a queue, and we need a desk. So that's an interesting list. What do other people think? Does anybody else have any other ideas? Oh, okay. Ian has ticket number, seat allocation, passenger ID. So that's another very interesting set of concepts. Okay. Any other suggestions? Okay, so let's go with these sort of two sets. I think there's a lot of interesting stuff happening here. Maybe let me first start with Ian's suggestions around ticket number, seat allocation, and passenger ID. So these are all interesting and important concepts in the context of managing passengers going through an airport and going onto flights, etc. There's two things about them, right? One thing about them is they're very specific to individual passengers at this point. They are not so much about the structure of the airport, right? So that is an interesting question: is what does our language focus on? Does our language focus on sort of modeling the booking process and modeling the allocation of passengers to seats, or is it actually about trying to capture the structure of the airport and how passengers flow through that structure, for example, right? And depending on where we fall on that divide, that decides what sort of concepts are important for us. For today's purposes, I think I would like to focus more on the structure of the airport. So I would probably be less interested in the specifics of ticket numbers and things like that. But if I wanted to model more the actual booking process and the process of how people get onto planes and find their seats and getting on the right plane and things like that, these kind of concepts might become quite relevant. Antonio has made an interesting number of, so Ian, yes, the sort of concepts that you've just put up here and the concepts that Antonio, I think, has put up, they're more about the structure of the airport, aren't they? So then they're probably more relevant for this domain. Antonio has just suggested that we might need passenger as well, and we're going to come back to that in a moment. Okay, but for now, I think an equally passenger generator, I think, Antonio, I'm going to leave out for the moment, and I'm going to explain why in a little bit. But let's start with the ones that you've suggested here. So we're going to start. We're modeling a whole airport, and so it probably makes sense, as you've suggested, to create a concept for airports, right? So we're going to add a class here in our meta model, and we're going to say this is our airport. Okay, and then we want if we look back at our slide here, the other things that we have are the check-in desks clearly, and we've got these queues. So it's probably worth again, as you've suggested, to put some classes in for those as well, right? So let's put in a class that allows us to model queues, and then let's put in a class that allows us to model check-in desks. Okay, there are lots of other things that we could model, but for now, let's perhaps just go with those for now. And there's suggestions still piling in on the chat, and that's really good. The other thing that's important about a meta model is that it describes the relationships between those things. So what relationships do you think would be important here? Any ideas? Owen Reynolds suggests desk has a queue. Yes, that's an important one. And Antonio, already knowing a lot about EMF, says airports contain queues and desks, right? So I think those are clearly important links. So let's put these, and I've chosen reference here to describe those links. And in fact, what I'm going to do is I'm going to hold down my control key while I click this, so that allows me to just do multiple ones, one after the other, without having to pick something up from the palette again every time. Click on here, and I'm going to say airport to queue, and then airport to desk, and those will become those things that describe that there's some containment thing going on. And then Owen, you suggested that a desk has a queue. And in fact, I think we would probably want to say, well, actually, it's also equally important to be able to go the other way. Okay, so to know what are the sort of the desks for the queue. Okay. Now, what it's done here is added these weird numbers for us, right? That suggests how many queues can be in an airport. Now, 0 to 1 would suggest there can be 0 or 1 queues, but actually, I think we want to say, no, actually, there can be an arbitrary number of queues in here. And I didn't like to call these queues rather than just queue. And so if I do this, then that just updates that. And similarly with the desks, right, there can be an arbitrary number of those as well in here. And then with these guys, so a desk can only have 1 queue, but a queue can actually feed into a number of desks. And we could say, well, actually, it does have to feed into at least 1 desk, and we could say that the desk has to have at least 1 queue, so exactly 1 queue. So we could make these changes as well if we wanted to. I'm going to make a few other changes, which I can't make directly in the diagram. In particular, I'm going to say, if I go to these properties down here, which for some reason doesn't quite work, I will say that this queue, this reference, is what we call a containment reference. So it gets this little arrow here. That sort of talks about the airport actually containing the queue. So if I move the queue into a different airport, it actually gets moved. It can never be in more than 1 airport. It's a part of the airport as a whole. And similarly, I'll do the same thing with the desks. This is just an important part of EMF models, that everything needs to be contained through a tree of containment references in our model. And with these guys here, I'm going to actually say, well, look, these are actually opposites of each other. And so I'm going to say, look, this is the opposite reference of the queue reference, and it then shows that quite nicely also as a double-headed arrow. Okay, so this is a nice structure. This allows us to, will already allow us to model the structure of our airport. Okay. What I'm going to do is I'm going to, as I say, be a little naughty and go and open one that I've prepared before, just to make sure I don't make any typos anywhere. And that's the one, that's the right one. So let me open that diagram, and hopefully that'll do the same thing. It almost does the same thing. Okay. Where has it put the other one? Let me just close that other project briefly so it doesn't get in the way later. Okay. So the only difference here, the only additional thing here is that I've given these check encounters names, which may or may not be particularly relevant, but it might help us if we wanted to differentiate them at a later point. An important thing here about this is what I have modeled so far is only the structure of the airport. Okay, Antonio, you had previously suggested passenger and passenger generator, and clearly, if I want to make my model do something, an important thing would be that I model how passengers move through this. Okay, but the person who only wants to describe an airport, they don't care about having to describe individual passengers. Okay, so it is important to differentiate between the DSML that allows us to give the structural description of what we're after, or the description of a particular behavior that we're after, a particular algorithm that we're after, etc., and the elements in that we need to capture the runtime state of a particular model as we step through it, as we debug it, as we make it do something. No, we don't have just numbers of passengers in each location. We will actually let's actually model an actual passenger in a moment. But what I'm saying is it's important to be aware that that's not actually really, if you wish, part of the language, in the sense that it's not when you create a model of an airport, you wouldn't want to have to draw individual passengers into various places, or even say there's 5 passengers here and 7 passengers there. That's only something that happens as you debug your model, as you step through your model. And so it's only relevant information at that point. And so we differentiate between the modeling language that allows us to generally model our airport and the runtime state of a particular model that shows us what this specific airport looks like at this particular step after we've done certain things in it. But in order to be able to do our model debugging, we need to include those aspects in our meta model, in our abstract syntax. Now, there's various ways in which we can do that. The GEMOC Studio actually allows us to model them as a separate meta model and then merge those together. Today, I'm going to be a little lazy and I'm going to just integrate them directly into this meta model here. And what we're going to do is we're basically just going to add a class for passengers. Okay, and we're going to say we have this passenger here, and then we're going to just say, where can passengers be at any given time, at any given point? Well, where can they be? Well, they can be pretty much anywhere here, right? So a passenger might be in the passenger queue at the moment. They might. Yes, Antonio. So it's a design and runtime meta models, exactly. And so the passenger might be in the check-in at the check-in counter, or in fact they might just be in the airport itself, right? And they might have just arrived but not decided for a particular queue yet. Okay, and all of these, just because of the vagaries of EMF, all of these need to be containment references. So that that's the one I want, so that we can have proper models. And we want to say, okay, well, there can only be one passenger, at most one passenger at a check-in desk. But obviously a queue wouldn't be much of a queue if it could only have one passenger in it. So we're going to say there can be an arbitrary number of passengers in our queue. Let me move this over here a little bit. And equally, come here. Equally, there can be an arbitrary number of passengers that are in the airport but haven't quite decided for a particular queue yet. Okay. Absolutely, Antonio, you could have, there's different ways in which we could model this, right? So we could create a location superclass here and then just attach the passenger to that. That's always so as with any design task, right? So we can vary this meta model, and different approaches will have different benefits and drawbacks. But absolutely, you're absolutely right. This is what I've chosen to do here, but that doesn't mean it's the only valid solution. It would be absolutely also a possibility to create a location superclass, and then make passenger be contained in that location, and make all 3 here be subclasses of that location class. That would also be an option. Okay. Again, just so that so one thing that is important is about this this runtime state thing. In order for GEMOC Studio to know what it needs to update in a model and how it needs to treat these, we need to actually annotate our meta model, tell it which bits are runtime state and which aren't. And for slightly weird historic reasons, we're doing this through an annotation in the MF model, and that annotation just has to be called aspect. And as I said, it's slightly weird historical reasons. The reason really is that you can merge these in, and that uses some aspect-oriented notions, and I think that's where that thing comes from. So everything that's part of the runtime state, so including these references, we need to add this annotation to. And I'm not going to do this manually for everything. What I'm going to do instead is I'm going to cheat again, and I'm going to hopefully be able to switch to this next state here. Okay, let's hope that my Eclipse doesn't crash in doing this, which it has had a tendency to do sometimes. Yes. Yes, come on. Okay, that looks promising. So this is the same meta model that we just had, just a slightly cleaned up version of it in terms of layout, and adjusting the names a little bit here. And you can see, as I said again, these annotations here everywhere. That is runtime state. Okay, what we do with this meta model, as I said, what we have now is we just have this diagram. That's all we have. In order to make this do anything, we want to have some classes, some code that can support us in doing this. And the nice thing is we can just generate this by clicking on generate and choosing all here, and that will generate a bunch of Java code for us, which the IDE and Eclipse can use to manage these models, to basically store models in memory, load them from files, store them into files, create basic files for us, etc. Again, I'm going to cheat a little bit, and I'm just going to step ahead in my Git tags here, so we can get somewhere. Yeah, okay, come on. And well, that's nice. It's actually gone and opened those projects for me straight away. So what this has done is it's generated some code in here, which is sort of just the code is just a class for every class in here, basically, so that we can store models in memory. And then it's generated some additional projects here that provide some basic editing support for such models. Now, this is all code that we've written. So in order to actually run it, what we have to do is we have to start a new instance of Eclipse that incorporates this code as plugins, so that we can actually edit our models. So that's, I think, what I'm going to do next for our next step in the tutorial. So I'm going to just go on here, and I'm just going to say run a runtime instance of Eclipse. So I've set this up previously, and what that does is it basically runs a version of Eclipse that has all of this code installed, as well as additional plugins. And while this is starting, let me start talking you through the next steps as well. So we've defined our abstract syntax for our language. Okay, it may be that I'm getting a bit sluggish here. Do tell me if you can't hear me anymore. We've defined our abstract syntax. Now what we're going to do next is we're going to define our concrete syntax. So we're going to define what our language looks and feels like, how it interacts with the user. Okay. And we wanted a graphical language. Okay, that means we want to draw diagrams to create models and to visualize models. So we need to think about what diagrams consist of. What is in a diagram? What's a diagram about? Well, a diagram fundamentally is, in computer science at least, tends to be sort of a bunch of nodes, and a bunch of edges between them. And the nodes might look differently, and the edges might have arrows on them or not, and might have labels on them. But essentially, typically, that's the sort of diagrams we mostly deal with. Not always, but mostly. And the Sirius platform that we're going to use supports these kind of diagrams quite easily. It allows us to declaratively describe these kind of diagrams and how they relate to an abstract syntax. So there will be nodes, and there'll be edges. The nodes typically relate to meta classes, to classes in our meta model. The edges typically relate to edges, to these references in our meta model, not always. And sometimes we might show links as containment. So we might have a box that contains other boxes, right? A node that contains other nodes. In addition, we then also need tools that allow us to create new stuff in the diagram or remove stuff from the diagram. That's something we won't look at today in too much detail. That's probably a whole separate tutorial at some point. So let's look at this a little graphically for a moment. So if this is sort of our diagram in general, right, this sort of our diagram pane, then what in Sirius we would do, we would define layers in this diagram that can be put on top of each other. And in each layer, we then define what are the nodes and edges that are available in this layer and how do they relate to the underlying model, to the underlying abstract syntax. So we might define, for example, for a state diagram, we might define that there are nodes that represent individual states and edges that represent transitions between those states. And then that is all wrapped up. There might be other layers in our diagram that do other things in addition. And that's all wrapped up in a declarative description of those layers. And from that, Sirius will then provide us with an interactive diagram. Okay, so let's try this. Let's try this out. So hopefully by now, I have here my runtime instance. Okay, so let me just. Okay, so this was our development instance of GEMOC Studio where we created the meta model, and from that we started a separate instance of GEMOC Studio that's our runtime instance that now has that meta model available. Okay, so one thing we can now do in here is we can create a new project. So, a new project that allows us to describe the structure of a diagram. Okay. That's what in Sirius it calls a, no, that's not what I want. A viewpoint specification project. Because Sirius talks about diagrams and things like that as viewpoints on the model, different viewpoints. Let's go with this simple name for now. Anything else I need to do? No, that's fine. And again, I've got something that we can pick up from Git in a moment. But I want to start us out building our own initially. Okay, so this is the main file that we're going to edit for this, which has sort of this nice sort of tree structure, and it's basically a collection of all the various viewpoints, all the various diagrams and things like that we might be able to support in our language. Okay, now we only want one viewpoint. We only want a diagram for our language. So let's create a new diagram. And then somewhere down here, I've got properties. This is where we define all the details of what this diagram is. Okay, so this would be an airport diagram, perhaps. And importantly, we say, what's the top level meta class in our abstract syntax that is represented by such a diagram? Okay, well, each such diagram, what do you think? What would each such diagram represent? Any suggestions in our world of airports and check-in desks and so on? Yes, Fazit, you can also just speak if you want, right? So you don't have to type it in. It's quicker. The airport, so Antonio suggests the airport floor plan. Fazit suggests airport, I think exactly, right? So we don't have a meta class for airport floor plans. So the actual meta class to go with this is this airport. And come on, go away. And actually there's sort of code completion here as well. So it knows about all the meta classes that are potentially available. And so we're going to say, yeah, that was the one we meant. Okay. And then within this, it's already created for us a default layer. So we can now populate that default layer with stuff. But before we do that, I just want to create a little example model so we can see the nice thing. One of the nice things about Sirius is that it sort of dynamically updates diagrams for us as we change this definition of the diagrams, and that's a really easy way of getting going with your diagram definitions. And so now we've got this basic thing set up here. Hang on, I think it's one more thing I need to do. I need to tell it. Do I need to tell it? I need to tell it that this is for our airport language. So I'm going to say, here's our airport language, and this is what this is for. And once I've got that, I can now just go and create a simple example project, which is going to be a modeling project. And in this example project, what I'm going to do is I'm going to create a new airport model. And that airport model, that wizard, is something that was generated from us for us from our meta model already. So we can just use that straight out of the box. The only thing we've got to say is that the model will start with a whole airport. If I do that, what it does for me is it creates this simple tree-based. It's created this sort of simple tree-based editor that I can use to just create the basic structure of my airport already, and so I can have a play with that straight away. So I've got a basic model here, but also I can now I should now be able to create a new airport diagram for this, because we've defined that for every airport there should be an airport diagram. And so I can say, okay, let me create a diagram for this, give it some name. And I get a diagram. So I've got my model here, I've got my diagram here. At the moment, the diagram doesn't contain anything yet, because we haven't actually specified at all what the diagram should look like. Okay, let me see, can I put this there? Then I should be able to do hello. Should be able to do this. Okay, so now we should be able to see all of these a little bit more reasonably. Okay, so if we now start adding things to our diagram, we'll see how these things get populated a bit more up there. Okay, so what sort of things do we need in our diagram? We need nodes and we need edges. What sort of nodes do we need in our diagram? Any suggestions? Passenger. We clearly need something about passengers. I'll leave passenger to the side for the little bit, but because we'll treat them a little specially. But we need something to represent passengers who are in the airport of haven't gone to a particular queue yet, right? We need queue nodes and we need sort of nodes for desks. Okay, so let's do those things. Okay, so we're going to create a new node. By saying new diagram element, we're creating a node here. We're going to do that, and we're going to create a node for, say, for the desk first. And then we need to associate that with a class, and I think we called those check-in counters, is what I ended up calling them rather than desks, in the canonical thing. Now that on its own doesn't actually do anything yet. Okay, so even if I add a new desk in here, okay, and save this, then nothing much happens here yet in the diagram, because what I haven't said yet is what this desk looks like. Okay, so Sirius differentiates between just defining the nodes that are there and then defining what they look like. And in order to define what this looks like, I have to add a style underneath it. Okay, and what I'm going to do is I'm going to add a very simple style that just attaches an image to it. Let me see. I think I can just get. Can I? Oh, okay. It's got to be workspace image. So let me just get that image into my project briefly. There. Can I get this? No, I can't. I hate Git. So here I would attach an image, but let me actually left that image. Obviously, I've left that image in my Git repository, which is in the wrong tag at the moment. So what I'm going to do instead is I'm just for this demonstration purposes, I am just going to add this as a little box here for now. And so there I can sort of define what color the box should be, what the label of the box should be, and we're going to just give this a label to say desk. Okay. So if I save this now, then immediately you see a little box appear here in our diagram. That's a desk, right? And if I add another check-in counter here and save this, then there's another check-in counter there, another desk box that represents that other check-in counter. Okay, and so in this way we can now sort of slowly build up our way through this. In the interest of time, given that it's sort of 1:45 already and we still have a few bits and bobs to go through, what I'm going to do is I'm going to jump ahead a little bit and show you what the result looks like and talk you through that rather than creating everything sort of click by click. So the principle is the same as you will see. Okay, so let me just close these briefly again and create. And then what I'm going to do is I'm going to get my Git to go to the and go to that next tag here, which is this one. Now I should be able to open my example projects here. So this is the same thing as before. Oh, wait. Let me open the diagram here again. Oh, go away. This is what I wanted. So this is a more complete diagram for a more complete example model. So this example model has a number of passenger queues, a number of counters, and a number of passengers in it as well. And our design, our actual language, the Sirius description of the design model here is this. And let me move this over there so we can sort of see them all next to each other. Okay. So what do we have in our design here? Let me keep this up a little bit. So we have our default layer, and then we have the check-in desks. And what I've actually done is I've added two different styles underneath here. Okay, the so-called conditional styles, each of which has a different image attached. And what that does is it checks this expression here to see whether or not there is a passenger at the desk. And depending on that, it will use a different image for our check-in desk. Okay, so if I have, say, a check-in counter here, and I add a passenger to this check-in counter, and then I save this, then you'll see that the image changes here to reflect the fact that this is now a check-in counter where a passenger is at that check-in counter. So I don't actually represent a new node for that passenger. I just show the fact that the passenger is there by using a different image for this node here. Okay. For the queue, we're doing this differently. So for our queue, for our passenger queue here, we actually have chosen to represent this as a node, but the node is a container, so it can contain other nodes. And so inside of that, we've defined a node that represents a passenger that's in a queue, and that passenger is represented with a certain workspace image. And this guy here is one of those guys, right? So this is a passenger that's in that queue. Okay. And finally, for the floaters, for the people who are somewhere in the airport, we've actually, rather than just throwing arbitrary nodes into this diagram, which we could have done, we sort of said, no, actually, there's going to be an area in our diagram where we capture those. And so we created a new node, which we've attached to the airport as a whole, and which is, again, a container. And so in there, we have nodes for passengers in there. which are attached to another image so that they look like they're sitting somewhere in the airport, basically. Okay, and then we have an edge definition here, which is this link between queues and desks. And you can see, if I click on this here, you can see that it maps from passenger queues to check-in desks. And it'll look at everything that's connected in that way on the model via this feeds into relationship that we've defined in our abstract syntax. Okay. Now there's one little bit that I need to do in order for, so this defines our concrete syntax. We can graphically edit our models. We can graphically play with them. And if we edit our models in this tree view, they'll get updated here. And if we spend a little bit more time, we could add tools to actually edit the diagrams directly. So that's all nice and all fine. In order to actually debug them, we need one little additional thing. We need to provide a little bit of Java code, which is referenced through this services class here. We need to provide a little bit of code here to basically tell Sirius that this one layer in our diagram, this default layer, might change over time as we step through the model. Okay. In order for this code to be picked up, it's no good if my Sirius specification is in my runtime Eclipse. It needs to be in my development Eclipse so that the whole project can be plugged into the running Eclipse. So what I'll have to do is I'll have to close this project here. I'll close my runtime Eclipse briefly and make sure that the project is in the development Eclipse, and then restart it so we can do the next step, which is about debugging. So I'm going to close this project here. I'm going to close this runtime Eclipse. Yes, and I'm going to go to my development Eclipse, where I'm going to open my design project. So this is exactly the same code. Both of these Eclipses feed from the same Git repository, so it's exactly the same code. But now, because it's in here, that Java code that I've just shown you briefly, we will be able to pick that up. And so let me then just run my runtime Eclipse again. While this is booting up, let me talk you through the next step. So the last step we need for a debugger, so that we can't just edit our language, our models, but we can actually do something with them as well. The last thing that we need is we need to define the semantics. We need to define the semantics of our language. And we need to define, if we want to debug through it, we need an operational semantics, which means it's a semantics that tell us how models change step by step as we make them do something, basically. Okay, so we need rules for how the models behave, and there are different ways of defining them. So in GEMOC Studio, you can have many different ways. You can define them essentially writing something that looks a lot like Java, or extend, I guess. But what we're going to look at is a declarative way of defining them using the Henshin graph transformation language, where we define rules that focus on the individual events that can happen in our airport models, and then together that allows us to generate a debugger from that. Okay, hopefully yes, here's my runtime GEMOC again. And we've got our example model still open here. That's fine. What we want is we want to create a set of these sort of Henshin rules that allow us to define everything that can possibly happen in a model. So again, as always, we do that in a project. So let's create a project. And what we're going to do is we're going to just create a general, just some arbitrary project. And we're going to just call this Henshin for now. And in there, what we're going to create is some Henshin rules. Henshin is an Eclipse project, again, which allows us to graphically define transformation rules over these sort of models. Okay, and I think Daniel wanted to come. I don't actually know whether he's here. Yes, he is here. So you've got Daniel on the call as well, Daniel Struber, who, if there's anything you ever want to know about Henshin, he's your man. Where am I? There. Yes, we want to actually tell it what it can use. Where's our airport? So we tell it these will be rules over our airport models. And finish this. Okay. I'm going to close this for now. So we've got. So this is a diagram again where we're going to define these rules. Okay. So we're going to take a rule and put it on there. What's the first thing that can happen in an airport? What's one of the first things that we should care about? Passengers arriving, right? I think that's a good thing, right? So let's write a rule for what happens when a passenger arrives. So let's call this passenger arrives. Okay, so what happens if a passenger arrives? Well, basically, in our airport, there's suddenly a new passenger. Okay, so the way we capture this is we describe in a Hessian rule the things that we want to find in the model, and then we describe how these things might change. And we describe all of this in terms of our abstract syntax. Okay, so we would say something like, look, if there's an airport, we use this preserve thing here to say that airport needs to already exist. We just want to find an existing airport. Okay, then what we want to do is we want to say, well, a passenger arrives means then we're going to add a passenger to this airport. Okay, so let's do this and and then, but we don't want to find an existing passenger. Instead, we want to create a passenger. Okay, and now we also need to actually link that passenger into our airport, right? It's no use having a passenger free floating somewhere. We want to say, no, that passenger is actually going to be in our airport. So what we're going to do is we're going to just say, well, look, it's a passenger that's in our airport, and that is a floating passenger in our airport. Okay, layouting isn't exactly the strength of Hessian diagrams. Feel free to complain to Daniel about this at a later point. So this rule now says, if there is an airport, it is possible to add a new passenger as a floating passenger in that airport. Okay, what other things might happen in our airport? So Ian, you suggest the passenger checks for the check-in desk. Yes. So if how does that work, right? How does a passenger check for the check-in desk? Well, they need to be in a queue. There needs to be a desk available, and then they can move from the queue to the desk. Okay. Again, in the interest of time, I'm going to move us forward a little bit on the Git repository here. I'm going to just say, let us switch to a tag that has all of these things already done. This can't go away. Okay. Because now I can close this and open this project. And so here I have the diagram that has all the rules that we need for our language. Okay, so we have our passenger arrival rule that we've already created. We have a rule for passenger picking a desk. So we have a passenger queue. There is a passenger in that queue. The passenger is in fact the first in that queue. And there's a check-in counter that passenger queue feeds into. And there's currently no passenger at that check-in counter. So the check-in counter is actually free. And if that's the case, then we can remove the passenger from the queue. That is, we delete that link between the passenger queue and the passenger. And we can create a new link between the check-in counter and the passenger, which means the passenger moves to the check-in counter. And if a passenger is at the check-in counter, they are eventually done and they move away from the check-in counter. And equally, if a passenger is a floating passenger, they will eventually pick a queue that's in that airport. And so they'll move from the floating passengers to that queue. If I say you're asking a really good question about how the order is defined, there is no order here, right? Anything that goes, goes. Okay, so that's important. So any of these things can happen. And actually, this is where things become really interesting. Okay, because what we can now do is with the GEMOC Studio, we now have all the bits and pieces that we need for debugging models. Okay, remember that example model that we had before? let's see how that behaves. Okay, so let's actually, I'm gonna just briefly show you how we set this up. So we say this is the model that we want to debug. This is the semantics that we need for this, and this is the visualization for it. Okay, so these AID files are files that Sirius generates to keep the diagrams in, and that's sort of all that we need by and large. And then we can sort of debug from there. Okay, that's going to take a little bit to get set up. Okay, yes, and what this has done now is it has analyzed all of these rules. It has analyzed the model and has understood what rules are currently applicable, but also which of those rules can happen at the same time. Okay, what things can happen concurrently? And so you'll see there's a lot of options down here of things that can happen. So individually, a passenger can arrive. There's a passenger at this desk, so that passenger can leave, etc. But actually, if I scroll down a little bit, we get to these much larger jobs, steps here where we can have things like that. Both of these passengers pick a queue, and this one passenger here picks another desk, or we could have other combinations of these things happening in parallel. Okay, and if I click on one of those and sort of say, let's pick this one, let's see what happens if we take this step. Okay, so if I do this, then the model updates, and we now see, okay, we've got these passengers in these queues, and this passenger has moved to the desk here, and stuff has happened. And so I can step through this model step by step. I can sort of say, okay, well, let's have another passenger arrive, and so on and so forth. In fact, I can even go back in time. So this view here, let me scroll down a little bit, shows me the various steps that I've gone through, and I can go back and go, oh, what if I had made a different choice before? Okay. Now we see there's a lot of steps happening here, but there's a lot of combinations of things that can happen in parallel, and that can become really confusing really quickly. So what I'm going to do is just as a final thing, so I'm going to say, well, actually, I'm only going to be interested in the steps that are sort of of maximum concurrency, where the most things happen at the same time. Okay. Let me see, this works. Yes. So what happens if I do that? Suddenly all of these thousands, well, not quite, but tens of different options that I have get reduced to the combinations of where the most things happen in parallel. I still get quite a few combinations because passengers might pick different queues and so on. So let's just do one of those and just see what happens, and think these passengers have left, another passenger has picked a queue, a passenger has moved to the desk, and so on. And so I can just step through my model step by step in this way without having to write any of this infrastructure. And that's pretty much me done. We've talked about this and done this. So just to conclude, we've looked at how we define the abstract syntax with EMF, the concrete syntax with Sirius, and how we can use Henshin and the GEMOC Studio to provide an operational semantics for our language, and use that to debug models in our language. Here's again the link to the airport language. There's lots of things that we haven't covered, other ways of defining semantics, textual languages, tools for model editing, etc. There's lots more that GEMOC can do, lots of other kinds of things that you can do, which I'd be happy to discuss with you, and some of which maybe can't do yet, but because it's a research platform, we'd be happy to explore. Now, there's a few questions on the chat. I'm going to start with Luca's question. Does GEMOC support time and timed properties for operational semantics? Ish. It supports whatever you want to do for your operational semantics. So if so one thing you can do, for example, is you can integrate a sort of a notion of a clock, and then explicitly in your runtime state, and then expand your rules to do that. There is no native support for time, but that doesn't totally stop you from supporting it. In fact, that's one of the things that I'm interested in is extending some of the Henshin stuff so that supporting time becomes a bit more native in there. DJ, what happens in case of conflicting rules? So that is something that the Henshin engine that I've shown you, this engine that I've shown you here for debugging will already take care of. So if it shows you that something can happen concurrently, it's because those rules don't conflict. And that's an analysis that it does in the background to check that they can actually happen concurrently. So for example, what it won't allow what's a good example in our case, it won't allow a step that makes the same passenger go to QA and a step that makes that passenger go to QB. It won't allow those to happen concurrently because obviously the passenger can really only go to one of those queues, and so it will give you two separate steps that allow you to say, well, what if the passenger goes to QA and what if the passenger goes to QB? But it won't give you a concurrent step where both of these things would happen at the same time, for example. Any other questions? Where can you get the materials? I think I will put the slides onto the platform and I'll attach them to the event there, and I'll also add the links to the airport language and to the Henshin engine and GEMOC and so on also onto that event so that you can pick them up from there. There's what's the paper? What is that paper? Can only see the link right now, so let me just click on that briefly to see what the actual paper is. Yes, so this is, there are lots of papers around the GEMOC Studio, and that is one of them, absolutely. So I'm not quite sure whether this particularly talks about time. I don't think it does, but I'm not sure off the top of my head. I would have to remind myself.
Can I just add something?
Yes, absolutely.
Sorry, I just sent this paper because it's about runtime monitoring, and it helps to define different rules to have these runtime properties when you're executing the models, and it's implemented on GEMOC. So I suppose maybe it's related to the question of Luca.
Yes, of course. Yes. So I think what this paper actually does is look at linking the sort of semantics you define that you can use directly in the debugger on the model to languages where actually the semantics is by compilation down to something and bringing that up again. But I think, but I'd have to look at the paper again to remind myself which of the many GEMOC papers it is. But I don't think there's currently a paper that explicitly talks about time as in sort of real-time time, real valued time in the GEMOC context. But it's possible. I just don't think, I'm not aware of anybody who's done it. Let's put it that way. That's perhaps the safest way of putting it.